In this video, we're going to do example 5. We're asked to use the concavity test to find the intervals of concavity for this polynomial function. The first step is to go ahead and find f double prime. Here's my function. F prime is 4x cubed minus 12x squared. F double prime is 12x squared minus 24x. Now, the concavity test says that if the second derivative is positive, the function will be concave up, and if it's negative, it'll be concave down. So what I want to do is do a sign test on the second derivative function. Right? When you put an input into a function, there are only 4 options with that output. It's either undefined, it's 0, or it's a number that's positive or negative. So what we're going to do in preparation for that sign test is we're going to find out where the second derivative is 0 or undefined. Now my second derivative has no domain restrictions. So there's no x values where the second derivative is undefined. However, in this case, there is an x value. Oh, nope, there's more than one. X value such that the second derivative is 0. Factoring out my greatest common factor between 12 and 24 is 12, and between x squared and x is x. 12x times x is 12x squared, and 12x times a minus 2 will be minus 2. Will be minus 24x. So the places where the second derivative is 0 are x equals 0 or x equals 2. And again, what that's done for me is it's partitioned up, divided up my domain into 3 subintervals, minus infinity to 0, 0 to 2, and 2 to infinity. There's only one of 2 choices. You pick a number in that interval, say in the pink interval, the second derivative is either going to be positive or negative there. Those are the only choices, and that's true for each one of these intervals. So here we're going to go ahead and do our sign test on the intervals. And here I gave us an extra line just to emphasize we found at these values that the second derivative is 0. There's no concavity there, but potentially a change in concavity. Okay, so I'm just going to pick a number less than 0, and I'm going to plug it into f double prime. I like doing that in factored form. So something less than 0, like minus 10. Minus 10 times minus 12, you can even write it. Minus 10 times minus 12 is a negative, and minus 10 minus 2 is also a negative. A negative times a negative is a positive. We are concave up. I'm going to do CC up for concave up. Right, my original function f. Pick a number between 0 and 2, like say x equals 1. 1 times 12 is 12, it's positive. 1 minus 2 is negative. A positive times a negative is negative, so my function is concave down on that interval. Now pick an x value between 2 and infinity, like 10. 10 times 12 is positive. 10 minus 2 is positive. A positive times a positive is a positive. So my original function is concave up on that interval. Now all I need to do is tell the reader we're interpreting these results. So my original function is concave up on these intervals, minus infinity to 0, union 0 to 2. Oops, Lindsay's dyslexic. Concave up. Here. Concave up. Oops. There. Let's fix that. 2 to infinity. And f is concave down on the complement of that set. 0 to 2. Okay. Now notice, without having to graph this, I can see that we have some inflection points, because right here at x equals 0, what happened? We changed concavity. I went from concave up to concave down. Similarly, at x equals 2, we had a change in concavity. We went from concave down to concave up. So what? So 0, comma, go find y, 0, comma, f of 0 is an inflection point, as well as 2, comma, f of 2 is an inflection point. All right, so here are our inflection points, which I was doing in green earlier. Zero, comma, we'll go find f of 0, which we can do in a second, and 2, comma, f of 2. Okay, so I'm plugging into my function f0 to the 4th is 0, minus 4 times 0 cubed is minus a 0, 0 minus 0 is 0. And then plugging in 2, what do we have? 2 to the 4th minus 4 times 2 cubed. 2 to the 4th is 16, minus 4 times 8. We've got a minus 16, I think. All right, so here we have it, 2, comma, minus 16. All right, so in summary, the concavity test is to find intervals of concavity. We really just want to know where the second derivative is positive and where it's negative. To do that, we need to get the second derivative. We need to find out where it's 0 or undefined. That breaks up the interval of the domain into subintervals where we can only be positive or negative, the second derivative. Often a table of values helps me organize this work, and I'm just picking x values in each interval, sticking it into the second derivative function, and that tells me about whether or not the original function is concave up or concave down. Again, it was a while ago, but we had talked about like acceleration being positive or negative. If acceleration was positive, my original function, my position function, was concave up. If acceleration was negative, my original function, my position function, was concave down. This table of values really does give us our answer, but it's nice to go ahead and summarize and say the intervals on where we're concave up and concave down. Where we change in concavity, going from concave up to concave down or down to up, those are places where we have inflection points. Remember, inflection points are on the original curve x. These are all x comma y's. Yeah? Excellent. We're done.